Okay, so welcome to section 3.1, which is complex numbers. So once again, this is review, right? We did this in trig, complex numbers. Oh boy. Numbers, let me write better. Okay, so let's note the imaginary unit I. The imaginary unit I is given as I is defined to be the square root of -1. Okay, and we consider I is just I. However, I squared, which is I times I, is going to be root 1 times root 1, or root 1 squared. Sorry, root -1 rather, so it's just -1. I cubed is I times I squared, so that's just going to be -1 times I. And I to the fourth can be thought of as I squared times I squared, or -1 times -1, otherwise known as +1. So what we have is a cycle, because once we get to I to the fifth, we can say, well, that's just I times I to the fourth, which is just I. Actually, let me do this in a different color. And I to the sixth will be I times I. Actually, yeah, I'll do I times I to the fifth, which of course is -1, because that's the same as I squared. So the cycle is then I to the seventh, momentito, let me do this, I times I to the sixth. So we get -I, and finally I to the eighth will be I times I to the seventh, or negative of a -I squared, which is +1. So there's a cycle here, and this cycle is let's see if I can get this. Ugh, well, okay, good enough for government work. So we know that it cycles I, so cycles the same four guys. It starts with I, -1, -I, 1. And we also have that I to the 4k is equal to 1 for all values of k, all integer values of k. That is whole numbers. And that's a k, not a kappa, for those of you that are actually listening to my lectures, not just printing out my notes. Okay, so definition. So a complex number, let me just, maybe I'll go off to the side. So a complex number, that's what we're going to define. A complex number, though we've defined it earlier, a complex number Z is of the form, Z is equal to A plus BI, where A and B are real numbers, and number 1, A is the real part because it's not attached to I. So the real part. And of course, b is the imaginary part because it is attached to I. The imaginary part. Imaginary part. So why am I using imaginary and not complex part? Well, imagine the imaginary unit, of course, is I, right? The imaginary unit, so hence the imaginary part. So let's note something about the complex numbers. So note the symbol for the set of all complex numbers, the symbol for the set of all complex numbers, analogous to that of all real numbers, the set of all complex numbers is what we call blackboard bold C. So much like R has a line through it, we have C with a line through it. So that's a math symbology for the complex numbers. So let's recall. From your trig class that the complex plane has two axes, hence plane. The real or horizontal axis and the imaginary or vertical axis. This is termed the x-iy plane. So instead of the xy plane, it is now the x-iy plane, because now the vertical axis is for the imaginary. So for example, let's plot the following. Complex numbers in the same imaginary plane. Complex plane, rather. Oh my goodness, I've got ants eating at my neck. Little vampires. Complex plane. Okay, so number one, let's say we have that z sub 1 is 3 minus 5i. The second number to plot, let's plot z sub 2. Let's have that be negative 4 plus 2i. Last but not least, let's do number 3. Third time's a charm. Z sub 3 is 2 minus 3i. Okay, so let's go ahead and plot x and iy. Let me make sure I say iy coordinate axes. So let's see, 1, 2, 3, 4, 5. Hopefully that's good enough. 1, 2, 3. So now this becomes the iy axis. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay, so we have z1, which has a value of 3 on the real axis, so that's a horizontal, and a value of negative 5 on the imaginary axis. So this is z sub 1. Okay. Similarly, z sub 2 has a real part that's negative 4 and an imaginary part that's positive 2. So I go to the left 1, 2, 3, 4 and up 2. So z sub 2. And last but not least, let's do this in maybe orange. So z sub 3 has a real part that's 2 and an imaginary part that's negative 3. Z sub 3. Okay, there we go. I think we understand that. Okay, so now let's review complex addition and subtraction. So complex number, addition and subtraction. Which should be straightforward, right? So let's let z equals to a plus bi. Maybe I should go down one line. That's gonna upset me. So let z equals to a plus bi and w equals to c plus di be elements of the complex numbers. Then number 1, z plus w. Well, if I'm adding these two, let's first add their real parts, a plus c. And then we add their imaginary parts, b plus d times I. And number 2, subtraction. If I have z minus w, that means from a's real part, I take away w's real part, to which I'm adding from z's imaginary part b, I take away w's imaginary part d. Okay, so each component is either added or subtracted, so note. The real parts are added / subtracted. Subtracted. To which we add always we add. Notice we're always adding in the middle here. The sum or difference of the imaginary parts. The sum or difference of the imaginary parts, respectively. Respectively. Okay. So let's now consider the following. So consider, should I have moved this over? I would like to give myself more room. Formatting. Maybe I'll move that over. Don't know what's too left adjusted. Okay, so consider. Let's have z equals to a plus bi and w equals to c plus di. Let me write that d a bit better. Di be complex numbers. So this would imply that z times w, actually, maybe I'll make w a different color so that it's easier for us to see which is which. So z times w is going to be quantity a plus bi times the quantity c plus di. And of course, if we FOIL that out, we get AC plus ADI. Actually, I'm going to put, no, I'll leave it like that for the time being. Plus BCI. I'll just keep the I. Well, no, I'll make it orange so you can see where I'm getting it. B times C times I. And finally, we will have plus BD times I squared. Okay. And actually, let me change all the I's. I think I will change all the I's to a different color. Let's change them to purple. Does that work? And we know that I squared is -1, right? So we know that I squared is -1. So what does this give us? This gives us, well, let's go ahead and do AC. What I'm going to do with the next two terms is I'm going to factor out the I that they have in common. So this will be AD plus BC. Oh wow, that plus became half purple. Okay, so AD plus BC all times I. And now we have a minus BD, right? That negative comes from the fact that I squared is -1. Okay, so now I can group AC and the negative, let me just copy and paste that, the negative BD together, because they're both real now, to which I'm adding the remainder here, which is AD plus BC times I. And if you recall, let's note, or recall, no, maybe let's note. An easier way to do this was, remember, if I stack the multiplication, so let's do Z is equal to A plus BI, and W is equal to C plus DI. Then together, what we get is that Z times W is going to be, well, let's see, let's look at the first grouping. Maybe I'll color code it. We know the first grouping is AC minus BD. Okay, so that's AC minus BD. And the way these look like negative signs, don't they? So we have our negative signs. Secondly, let's do the second part maybe in, what color shall we use? I've already used purple. Oh, green. Don't really. Maybe pink. I do like pink. Okay, so the second part we know is AD plus BC times I, right? So where do we get the pink guys from? Well, AD plus BC, and notice that this cross multiplication thing that I have here kind of looks like a plus on its side. Okay, so if we set up our multiplication like that, we should be fine. So let's go ahead and do an example. So for example, so let's let Z be 4 plus 3I, pardon me, and W be -2 plus 5I, let's find number 1. Let's first find z plus w. Okay, so I'm going to call z blue. So z is 4 plus 3i. And let's call w purple. And w is negative 2 plus 5i. So if we're looking for the sum, z plus w, what are we going to get? Actually, maybe I'll skip a line. So z plus w, all I'm going to do is I'm going to combine their real parts. So this will be four plus a negative 2. And then I can combine their imaginary parts. So that's going to be 3 plus 5 times I. So this gives us, well, 4 minus 2 is 2, and 3 plus 5 is 8. So 2 plus 8i. So now number 2, let's go ahead and find the difference. So z minus w, let me go ahead and copy and paste this. Copy, paste. Okay, so now we have z minus w is going to be, well, now I just take the difference of their real parts. So that's going to be 4 minus a negative 2. So minus a negative becomes plus. To which I add, I always put an addition in the middle, I add the difference of their imaginary parts. So this will be 3 minus 5. So what I end up with then is 6 minus 2i. And last but not least, let's find the product. So number 3, z times w. Okay. So what we're going to do, z times w. So first we're going to find the subtraction with the 2 subtraction lines. So we're going to have 4 times negative 2 minus, because those look like subtraction lines, 3 times 5. Oops, 3 is blue. 3 times 5. And then what do we do? Then we add the addition part, right? So now we're going to do the part that looks like addition. So it's just going to be, let's do 4 times 5. The cross addition, right? Plus 3 times negative 2. Okay, so what do we get here? We get negative 8 minus 15, to which we're adding 20 minus 6 times I, rather. Okay, now let's make sure we did that right. Negative in the first component, positive in the second component, right? So hopefully we did this okay. So what do we get now? What's that? Negative 23 plus 14i. And would that work out? Negative 8 minus 15. Then 20 minus 6. Yeah, it does work out. Doing it the old-fashioned way. Okay. So definition. Hopefully those make sense. So definition. Okay, so the complex conjugate. The complex conjugate. That's what we're defining. Of z equals to a plus bi is given by z bar, let me make that clear, z bar is equal to a minus bi. So that is, i.e., the sign of the imaginary part swaps. The sign of the imaginary part, imaginary part, changes. If it's positive, it becomes negative, or vice versa. If it's negative, it'll become positive. So now let's consider, growl, I know, consider let's say we have z equal to a plus bi, and then z bar being the conjugate, complex conjugate, a minus bi. Then the product is zz bar okay, well, first we're going to do the negatives, right? So that means these look like negative signs. So we're going to do a times a. So do you agree that that's a squared? A squared. Then we're going to do minus b times negative b. Well, b times negative b is going to be minus a negative plus b squared, right? Two negatives make a positive, and there's no parentheses there. Then we're going to add to that the addition part. So it'll be a times negative b, which is going to be a negative ab. And then we're going to add to that a times b, a times b, and that's the imaginary part. But notice that these two sum to 0, so we're left with the fact that zz bar is simply a squared plus b squared. And that is a real number, right? There's no imaginary parts left. So let's note that. So note. Z, a complex number, means that z times z bar is a real number. So, hence we can use this to rationalize. Hence, we can use this fact to rationalize the imaginary unit I being equal to the square root of -1. You know, that's a terrible square root symbol. The square root of -1 in a complex number quotient. Complex number quotient. Okay. So let's see what we do. So let's consider if I had two complex numbers. So consider once again, let's have, maybe I'll go down here, I'll need the room. Z equals to A plus BI, and W equals to C plus DI. No, not W. Oh yeah, W. I've already done the complex conjugate. So W equals to C plus DI, just some random other complex number. Doesn't matter what it is. So if I am asked to find Z divided by W, Z divided by W, what do I get? I get A plus BI divided by C plus DI. But in order to rationalize that I in the denominator, I would need to multiply top and bottom by, let's do blue, the complex conjugate of the denominator, which will be C minus DI in order to rationalize. So C minus DI. Okay, so what do we get? Okay, so multiplying the numerator, we know that we'll get, for the real part, maybe I'll just keep it orange. We know we're going to get AC minus a negative, so plus BD, to which we're adding AD, which is now negative. Let's go back up. Let's make sure we've got it right. AD plus BC, right? So AD, but now AD is negative, plus BC. So I claim that this will be BC minus AD times I. And this is all over. Well, I know that the denominator now is a difference of squares, right? It's going to be C squared plus D squared. I mean the sum of squares. Did I say difference? Shame on me. The sum of squares, because this is complex rationalization, right? Okay, so let's define this formally for the quotient. So division of complex numbers. Division of complex numbers. Okay, so once again, let's let Z equals to A plus BI and W equals to C plus DI be elements of the complex, or be complex numbers. Then the quotient, then Z divided by W is going to be AC plus BD. So notice now we have the sum as opposed to the difference, plus BC minus AD. Now we've got a difference here, so we've swapped sum and difference, and we've swapped places in the second component, all over C squared plus D squared. Okay, so let's use this definition of division for the following. So example, so find the quotient. The quotient for the given complex numbers, or for the following. No. Find the quotient. Let me be explicit. z over w, z over w for the following. Okay, so number 1, let's say we have that z is, let's do 2 plus I. Oops. 2 plus 1 times I, and w is going to be 4 plus 3i. Okay. So let's have z be blue. So z divided by, let's have w be orange instead of purple. Something different. W. Okay, so now I know I have addition for my first component. So let's look at it. A times c. Would it be easier if I put them vertically? Probably. But a times c is real times real. So that's going to be, do you know what? Yeah. Let me go back. Let me write them out in their colors. So z is 2 plus I, and w is 4 plus 3i. So together their quotient will be, so z over w. Let me color code. So in the numerator, we first have the sum, AC plus BD. So AC will now be 2 times 4. What used to be our difference has now become our sum. Plus 1, that's a 1 there next to the I. It's implied 1 times 3. Now we always add, but now we're going to add a difference. And in particular, the difference is BC. So I have to do this way first and then the other way second. Okay, so for us, BC is going to be 1 times 4, from which I'm subtracting now, not adding, the product of the other diagonal, which is 2 times 3. And that is my imaginary part in the numerator. All over what amounts to 4 squared plus 3 squared. Okay, so what do we get when we do this? Well, this looks like it's going to be 8 plus 3, to which I'm adding 4 minus 6 times I, all over 16 plus 9. So this is what? 8 plus 3 is 11. 4 minus 6 is negative 2. All over 16 plus 9 is 25. So usually the book likes to see a plus bi. So written in pieces, this will be 11 over 25 minus 2 over 25 times I. Okay. Don't really have, do I have enough room? I don't know. Yeah, I think I'm going to go down to the next page for part 2. So subscript number 2. Let's say we're given that z is equal to 4 plus 3i, and w is going to be 2 minus 5i. I didn't repeat any of the ones I've already done. No, okay, good. So let's rewrite these. Maybe this time I will use blue and purple. So we have that z is 4 plus 3i. And then we have that w is 2 minus 5i. Okay, so z divided by w is going to be remember the first part is now addition. So it's going to be 4 times 2, the first. You know what, there's so much noise coming outside. Hold on a moment. Okay, so the first, guys, will be 4 times 2. To which I'm now adding as opposed to subtracting. The second column is 3 times a negative 5. To which I'm now adding a difference, right? So the difference is going to be BC. So 3 times 2. From which I'm subtracting AD. So that's 4 times a negative 5. Pardon me. It's supposed to be a negative 5. Negative 5. All times I. Divided by 2 squared plus. Now here's the caveat. It's negative 5 squared. Now we have to include the negative 5 because it's w times w. So both is negative. Okay, so what do we have then? 4 times 2 is 8. 3 times a negative 5 is minus 15. Plus a quantity, 3 times 2 is 6. Now minus 4 times minus 5 is positive 20. Times I, all over 4 plus 25. Yeah, I did it all in pink. Okay. So what does this give us? It gives us a negative 7 plus 26 times I all over 29, which your book would prefer if you broke up into A plus BI, which will be minus 7 over 29 plus 26 over 29 times I. And last but not least, number 3, let's see, where shall I put this? 2. Okay, so let's say we have that Z is minus 3 plus 5I, and W is 2 minus I. Okay, so this time let's have Z still be blue. Minus 3 plus 5I. Maybe I'll move that over to the left a bit. And let's have W be dark yellow. So W is going to be 2 minus I. And of course that's 2 minus 1I. So the quotient, Z divided by W, is going to be, remember, for this, it's going to be a sum in the first component. So it'll be negative 3 times 2, to which I'm adding the product 5 times a negative 1. That's my real part. Now let's add to that the difference. BC is going to be 5 times 2. And I'm going to subtract from that negative 3, so that becomes plus 3 times a negative 1, AD. And that's all times I. Let me draw that parenthetical a bit better. Okay, and then of course we'll have 2 squared plus a quantity negative 1 squared. It's always going to be positive. 2 pluses regardless in the denominator. Okay, so what do we have then? We have negative 6 minus 5 plus the quantity 10 minus 3 times I all over 4 plus 1. So this gives us minus 11 plus 7I all over 5, which we can write in a plus b form as minus 11 over 5 plus 7 over 5 times I. And there we are. I'll see you guys in the next section.